The topic of today is how to set meaningful passed-failed limits, how to get there, and getting some additional hints on it. My name is Markus Becker. I'm the technical director here at NTi Audio, and sitting next to me is Gregor Schmidle, our product manager. He will take care of your questions and answer to them. The topics we have prepared for today is a short introduction about the scope, providing an overview about what we're going to present to you. Then we're going to introduce you to the limit definition procedure, followed by some words about the result curve display, which has also a major impact in this tolerance limit process. We have also prepared a practical presentation and follow with some additional practical hints on the whole procedure. At latest at the end, we will take care of your questions and provide some auxiliary information. The overall duration of today's webinar will be in the region of around 30 minutes. On this picture, on this graph, you see a selection of typical electric or electroacoustic devices that need to be tested in production. I have chosen them to visualize that they have, of course, different complexity, they have different costs, and depending on this complexity and on the costs, you will pursue different approaches, different strategies to establish passed-failed limits in a production. For instance, a complex integrated circuit, of course, requires a lot more of measurements, of tests, as a simple speaker module for a mobile phone. Well, for this webinar, we decided to restrict ourselves on the simple and rather low-cost products. The reason is because these products are very typically very little or even not specified at all by the product owner. So imagine you are a test engineer at a contract manufacturer. You get the production data for manufacturing such mobile phone sub-assemblies with an integrated transducer. But the product owner does not inform you at all about how to test this device, what measurements to execute, what are the acceptance limits. But, of course, he expects that you are providing good quality. So what do? You have to find some way for testing and reasonably sorting out bad samples from your production line. But keep in mind, it doesn't have to be a device like that. It can be any electric or electroacoustic device. It can be even a device that generates a sound by itself, maybe a machine which generates a repetitive sound, which you want to verify, which you want to monitor over time to make sure that there are no deviations. So this is just an example what we're going to present to you. The goal, however, is always the same. We want to make sure that the good operation is detected correctly, is passed through the test, whereas any defect, any fault is detected reliably. We want to avoid that good working samples would be rejected by the test, and we want to avoid too, of course, that faulty, that defective devices would slip through. The procedure that we propose to you looks like that. In the first step, we're going to have to set up the test system. Then we have to somehow establish the reference data by having said that there are no test definitions, no specifications available at all. We somehow must base our decision on some reference data, so how to get there. Then, as mentioned before, we have to decide how to display these results, because that has an impact as well. We may add some classes. I will explain you later what that means. And in the end, when our production has been established and is ramping up, we should probably execute some fine-tuning and monitoring of the process. So phase one means set up a test system. It can be, for instance, our FX100 audio analyzer that has been specifically optimized for production testing, can be another device to test audio products. Just please make sure that it is a reliable and accurate system, that it is calibrated correctly, because of course, you want to make sure that you have correct test results, correct measurement results. And then you should also take care that the test jig itself, especially if you are dealing with acoustic testing, that the test jig has been designed properly, adequately, and that the cabling is correct and in good quality. Next, you have to select the test signal by which you're gonna verify the proper operation of your device under test, and you have to parameterize this test signal. Maybe your device under test generates a sound by itself. That would be an alternative, but normally you have to generate a test signal, feed it through the device under test, and then measure the output. This test signal can be, in a very simple case, be a single tone, single sine tone, can be a sweep. Actually, we at NTi, we strongly emphasize the glide sweep, which is, to our opinion, the most powerful test signal for audio testing. Or, of course, multitone or other alternatives like pink noise, depending on the application. The glide sweep that you see here schematically has the big advantage that you can adjust the bandwidth of the test signal. You have a big freedom to adjust the level, even in different sections over this bandwidth of the test signal, and you can also squeeze the duration down to the absolute minimum of a few hundred milliseconds or seconds, depending on the application, and this is very helpful, especially in high volume production applications. And last but not least, you have to make sure that you are applying relevant measurements, meaning measurements that are able to unveil the actually occurring defects in your device. If you execute a measurement that measures something which never goes wrong, I mean, that doesn't make sense. It's just adding complexity to the whole setup. So please, this is something you have to really do for your device individually. Find out what are the relevant measurements, those that allow you to properly, to reliably unveil possible defects. Typically, this is level measurement, for instance, frequency response. If we're talking about modules, assemblies, the impedance test is a very helpful measurement, and with some sub-information like resonance frequencies and so on. We always recommend also to apply a test that allows you to detect audible defects, which are not detectable by level measurement, for instance. So our pure sound steepness measurement is one of these possible solutions, or harmonic distortion analysis would be one. And then there are, of course, more like phase or crosstalk. That depends strongly on your device under test and its characteristic, whether these measurements make sense or not. The next step is, as I said before, we have to establish a database which allows us to build the tolerance limits upon. Here you see a graph with a number of recorded frequency responses from a specific type of module, acoustic module, and you have seen I have colored some of these curves. The green curves would be those where I would say on a first look, okay, they look pretty similar, so this seems to be good working devices. I mean, there is a certain fluctuation or discrepancy, for instance, in the low frequency range, but it is a rather low cost device, so this is quite typical. It's not a high precision device. However, the yellow curves are somehow a little bit off this typical behavior, especially in the higher frequency ranges. So we would call them borderline samples. It's not yet clear whether they're passed, whether they're good, or whether they're bad and needed to be rejected. So it's maybe better to identify them and double check them at a later point. And then we have the one red curve that apparently represents a sample that is behaving completely differently or mainly differently. So this is a sample where I would say, sort it out. This is a bad sample. This should be rejected during the test. So the first step is acquire this data. Next, we take those samples, the results of those samples where we believe they are working fine, and we add a tolerance headroom, for instance, plus minus 2 dB to this reference samples, actually to the maximum, in this case to the maximum and to the minimum recorded curves. And this gives us now, you see this light green band, the initial tolerance limit. Now, before we apply these limits, just some words about how to display the display mode of these result curves. If you are working in a lab, you are probably used to using absolute curves, absolute results, as you can see on this plot. This is a very good approach for high precision devices. High precision meaning that the deviations from sample to sample are very small. Most, or let's say all samples behave almost identically. And in that case, of course, the absolute approach is, or the absolute display is a good approach. I have, by the way, here also shown with the orange curve the behavior of a golden sample. It may be that the product owner has provided, let's say, a really good working device and says, okay, that's the way I want to have my products. Then you can use this device. Maybe you have sorted out it yourself. You can use this golden sample as the only reference for building your tolerance limits. And all further production samples, of course, should behave very similarly, should be very close to these results. However, when we talk about low-cost mass products, you may notice, for instance, that, let's say, batch number 1 has the transducer built in with the transducer coming from manufacturer A, and the next batch of modules that you get comes with a transducer from another manufacturer, and there is a slight discrepancy in the behavior of these two different transducer types, of these two different transducer manufacturers. So how do you cope with that? Actually, our answer is we recommend to go for the relative curve display. What does it mean? It means that we fit all recorded curves through a reference point. We are looking for a point where we think the behavior of the devices is very stable, for instance here at 2 kilohertz, and we say now, okay, the level, the sound pressure level, for instance, or the measured level at 2 kilohertz, that is our 0 dB reference. So when we, for instance, get another sample, a new sample, which on an absolute scale would have a higher sound pressure level, this curve will be shifted downwards so that it fits exactly to this point. And now you can see the advantage is that only the shape of this curve, the shape of the result of the measured sample, is relevant for the decision whether it's within the tolerance or not. And in practice, it means, for instance, talking about our example of mobile phone sub-assemblies, it doesn't matter whether one sample is a little bit louder, 1 or 2 dB than the other one, because the customers will anyway not notice, but it is important that they behave in a similar way. And by this way of displaying and verifying the curves and the relative display, we make sure that these fluctuations are minimized or become obsolete, so there is no risk of rejecting these samples if they have a higher or slightly lower sound pressure level. The behavior, this type of behavior, is the decisive point. Now we come to the fourth phase, the classes. What does that mean? Let's assume we have now selected our reference curves, we have established our tolerance limits, and we make the first measurement, or one of the first measurements. We get a curve that is again close to that, but it is actually missing the acceptance band in few points, slightly missing. So if we look at that, we would say, come on, this is really not bad. This is most probably acceptable. But somehow we must have a mean to identify these samples, because the sample that is clearly behaving differently, of course, should be rated fail. But those that are very close but not really in the tolerance limit, they should be identifiable. So for that reason, we recommend to add a second band, actually below and above of the tight limits. We have colored it here in orange. And if a sample partly falls into this second class, then we know, okay, this is a borderline sample. Maybe we have to take a closer look at it, but at least it helps us to identify these samples rather than those who would even exceed the red lines, so that would be really fail because they are too far away from the behavior of our reference samples. So adding this class is a very helpful, a very powerful feature to identify these borderline samples, which are a good help for our fine-tuning process. Okay, we are ready to start with the practical presentation. The setup I have here on my desk comprises a FX100 audio analyzer, which feeds the test signal through an amplifier to our mobile phone subassembly with a built-in transducer. From there, the sound is acquired through an acoustical coupler with a microphone back to the FX100 for the measurement. This mechanical handle here is something that is quite typical and even in use in production sites. So I'm gonna switch over to the software that runs this test setup. What you see here now is our RT speaker software, which has been specifically optimized for testing acoustical devices in a mass production. And we are here in the reference mode. Reference mode means here we are acquiring the result curves of our reference samples without judging them. So there's no pass-fail decision in here. It's just an acquisition mode. And you see I have already recorded 10 samples, and I'm going to add now some more. So you see the sample here has quite typical behavior, very close to the ones I have already recorded. So I would say this one is okay. So let's add another one. Well, this one is apparently behaving completely differently, especially here in the impedance response. You see the curve has a completely different shape like all the previous curves. I can also show you that in a large scale. So this is a sample I would not use as a reference data. For this reason, I delete it from my reference data. And yeah, let's assume that we are now in a stable condition. I quit the reference mode. Of course, I save all my data and I create the tolerance limit. Actually, the system calculates them for me. I have already defined the headroom, the 3 dB or whatever headroom from the reference data to the tolerance limits. And the result you can see now in the production mode. Here you see, if I enlarge that, for instance, frequency response, the two inner curves represent the tight, the truly passed behavior, and the outer ones would be the second class to identify borderline samples. So again, let's test some samples here. So this one passes the frequency response. Here in the impedance response, there seems to be a problem. Okay. The second one, the next one I took, you see here in the frequency response, it misses the tight limits, but is still within the second class limit. So this is what I call okay. So this is, for instance, now a typical borderline sample. Same with the impedance response. Here you see that's a point where it behaves differently from the previously recorded reference samples, but not that far away that we would say it is a failed one. So let's test another sample. Yeah, this one is apparently very bad. It misses the limits, all the limits from the frequency response. It clearly misses the impedance response. So that is correctly identified as a failed sample. The borderline samples, by the way, can be used now to fine-tune these tolerance limits. You can use them to you can add them to the reference database, recalculate the tolerance limits. So first of all, of course, you must make sure that the borderline sample is acceptable. But if it is, then you can add it to the reference samples, and that will widen, of course, a little bit your tolerance limits, but that will allow you to better identify correctly all good working devices. So let's go back to our presentation. Some additional hints that I would like to give you. There is, of course, always the question, maybe I just raised it, how do we judge a borderline sample? How do we decide whether it is still acceptable or whether it is already to be rejected? And the answer is, because we do not have any information from our product owner, the answer is we have to listen to it. We have to make up our own mind. We have to decide ourselves whether we want to accept it or not. So listening to the sample is very helpful, especially because it allows us to identify annoying, irritating sounds, annoying effects. Our ear is very sensitive to that, like the pure sound test, the rub and buzz test that we are providing with our system, but listening to it is a very proper way to identify this behavior. If you are still in doubt, compare this borderline sample to other devices, and yeah, that should allow you to make a final decision whether you want to put it in the passed or in the failed bin. Another aspect is this fine-tuning, which I mentioned already before. If we have now identified our borderline samples, we can both use them to fine-tune, to adjust, to optimize the tolerance limits, or B, to verify the proper operation of our test in a production. So a borderline sample that would be rated as failed, of course, must be rated failed by the test itself, whereas the borderline samples that would be accepted should pass the test. And the third part that we recommend is the process monitoring, especially in the early stage of the ramp-up phase. What does it mean? We recommend to select a single value result, for instance, sound pressure level at a specific frequency or a resonance frequency. Could also be TLS small parameters if we are talking about loudspeaker testing. And then plot them again on a scale against the time. So you see that here all the red points are hundreds and thousands of samples of measurement results from samples that are plotted versus time. And here you can see there is a certain fluctuation. There is a second curve, the blue one overlaid. The blue one represents the ambient temperature. Now this gives us, for instance, the hint that there is a certain dependency of this measured behavior from temperature. And that brings us to the conclusion that we should probably recalibrate our whole test system from time to time, especially if the ambient temperature changes by maybe 2 or 3 degrees, just to make sure that this effect is compensated. But also in the long run, this trend analysis gives you a very valuable feedback on negative trends to identify them as early as possible. A very sophisticated way in this aspect is the CPK-PPK process control analysis. This is a mathematical method to identify fluctuations short-term or long-term from a production.